Most people look at a Raspberry Pi and see a toy, a low-power, single-board computer built for weekend hobbyists, to blink an LED or run a lightweight ad blocker for their home network. But look past the exposed pins. If you apply strict software architecture principles to this constrained edge hardware, it becomes capable of running a unified operations layer. This diagram maps out a complete operational stack. At the very bottom, driving this entire architecture, you only find 3 pieces of physical hardware: a standard router, a miniature ASIC miner, and a single Raspberry Pi 4. We are looking at a functional micro-NOC, a personal network operations center. It is a centralized infrastructure that manages everything from quantitative financial portfolios and algorithmic trading bridges to a fully synced Bitcoin node. Pushing edge hardware to this level of concurrent complexity requires abandoning bloated enterprise design. You have to build from first principles, writing modular, compartmentalized microservices, a process that modern AI coding tools have compressed from years of work into a matter of weeks. Any persistent server environment, whether in an Amazon data center or on a desk, lives and dies by its network connection. If the uplink drops, the entire stack goes dark. The catalyst for this specific architecture was a highly unstable dormitory internet connection. The network frequently dropped off, and reconnecting required manually clicking through a captive web portal login screen over and over again. To solve this, we map out the first architectural layer on your diagram, the NetGuard Stack. This script isolates the network monitoring logic onto the Pi, positioning it directly behind the WAN router. It operates on a continuous local loop. It consistently pings the outside network to verify connectivity. The moment a packet drops, it triggers a curl command to automatically push the correct credentials to the dorm's login portal, restoring the connection and logging the uptime without human intervention. Automating this specific login sequence ensures that software-level authentication hurdles no longer stall the system. This creates a more reliable network bridge, allowing the Pi to maintain its data feeds and remote access without constant manual intervention. With a stable uplink secured, we can start layering complex, discrete operations onto the Debian Linux operating system. We do this by treating every new function as an asynchronous microservice. Looking at the new additions to the diagram, column 2 represents the QuantStack. This module runs scheduled Python scripts that query external stock data providers. It utilizes pandas to process the raw numbers, calculates the portfolio's exact hedge level, and pushes the valuations up to Google Sheets. Operating separately from that financial logic is column 3, the BTCStack. It continuously communicates with the broader Bitcoin network to maintain a fully synchronized Bitcoin core node, an Electrum server for private wallet indexing, and a TOR hidden service. They write to the same local SQLite data logs, but their active processes never cross paths. This strict separation acts as an architectural failsafe. Because these modules are compartmentalized into independent scripts and Docker containers, a broken API key that crashes a Python financial model will never interrupt the blockchain sync on the Bitcoin node. Scaling multiple advanced workflows on hardware with limited CPU and RAM requires this exact kind of struct modularity. It guarantees higher stability, ensuring one faulty process cannot trigger a system-wide collapse. So far, the Pi has only processed data internally. The next challenge is utilizing it to monitor and control hardware that physically exists outside of its own casing. We extend the diagram with column 4, the MinerStack. This actively queries a physical BitAx ASIC miner on the local network, tracking its temperature, power draw, and hash rate metrics in real time. Then we face a geographic problem. We need to track the status of algorithmic trading bots, or expert advisors, that are running on remote Forex virtual private servers housed in off-site data centers. To bypass external firewalls and safely route that data home, we implement a reverse SSH tunnel. This creates a secure, persistent bridge that feeds the remote server alerts directly into column 5, the VPSBridge on the local Pi. The Pi now functions as a central command hub, bridging local hardware with global virtual servers. Managing this many concurrent systems creates a massive influx of data. A single developer cannot constantly monitor Linux system logs, trading bot alerts, and blockchain synchronization states at the same time. This layout shows our telemetry layer. The system scrapes metrics from every stack and visualizes them on Grafana dashboards, providing real-time readouts of network latency, node synchronization, and miner temperatures. But detailed charts demand active attention. For immediate control, the entire architecture routes its outputs to a single asynchronous interface, the Telegram ops layer. Look closely at these mockups. Entirely different events, a sudden internet drop, an offline ASIC miner, or a morning hedge fund brief, are translated into standardized text alerts sent directly to a mobile device. Centralizing these notifications into a conversational interface solves alert fatigue. It takes the noise of 5 different operating environments and refines it into a clear, actionable command center right in your pocket. Historically, architecting a system that spans Linux network protocols, financial APIs, and blockchain RPCs required a team of specialized engineers. A solo developer attempting this would spend months just reading separate documentation, wrestling with cross-language syntax, and manually debugging integration errors between Bash, Python, and Docker. By integrating modern AI coding tools into the workflow, that friction disappears. AI changes the developer's role from a syntax writer to an architect. The AI acts as the execution engine, taking a multi-domain project that once required years of specialized coding and compressing the deployment timeline to roughly 6 weeks. This complete diagram illustrates the final data flow. Raw external inputs enter at the bottom, move up through the isolated modular processing stacks, and are ultimately synthesized and delivered outward to the user's phone on the right. Substantial operational capacity does not require sprawling, expensive server racks. It is achievable using consumer edge hardware, open-source Linux tools, and AI-accelerated development cycles. Pre-packaged enterprise appliances offer similar features, but they lock you into rigid ecosystems. You cannot tear them down, inspect the source code, or force them to integrate with your personal specialized workflows. The true value of this micro-NOC is its foundational extensibility. It provides a sovereign, modular blueprint ready to scale alongside whatever new operational challenges the user faces next.